Okay.
All right, continue with my scatter approach. Here I'm going to question the cosmological Doppler redshift. And actually I joined the, what was then the Natural Philosophy Alliance, I think about 4 or 5 years ago. And I mean, probably like most of you, any physics you had in school, etc., was always relativity. And it was interesting. I mean science fiction books, time dilation. I remember as a kid, they had the Time Life series. And I bought a book on time, and it was just so interesting that the speed of light was constant and it wouldn't catch up and all this type of stuff. So I never really had any reason to question it. And then for some reason, I guess I was interested in trying to understand the twin paradox. And all the explanations I would find of it were, well, it's because the spaceship is accelerating, therefore that's why his clock slows down, but the Earth clock doesn't slow down. However, you only know that at the end of the trip. And while you're watching it, both guys see the other guy's clock slowing down, etc. And, I understood how they got the derivations, etc., but it just always bothered me that they always had to say, but the difference is this acceleration. And then I would see other websites that say, well, get rid of the acceleration, just have them pass each other at constant speed, or put in a third spaceship or something like that, and then it breaks down. So I started looking, I said, is there something to this? And I came across, the first website I came across that had a lot of questioning is Paul, those who are familiar with Paul Marmot, was a Canadian physicist. I think he died in the mid-90s, but he still has a website. I think it's called Newton Physics. And he wrote about 20 or more papers on, kind of like me, all different topics. And one of the ones that got me interested was, I don't think he called it tired light, but he had a theory that the reddening was due to Compton scattering. And I know the mainstream will say, well, if there's Compton scattering of light rays, then they have to blur, and since the supernovae don't blur from, supernovae 1As from distant galaxies don't blur, therefore tired light is wrong, and galactic expansion is right, and all this type of stuff. Yet I've seen a number of websites that say light could get re-emitted when it's absorbed in the same line, and there'd be no blurring. And Paul Marmot had a lot of different, he wrote on a lot of different things, relativity, etc., etc. That got me interested, and I started finding other websites. I discovered the NPA, and I went to my first conference from Maryland, so it was easy for me to go to the 2011 conference, which was there. I actually wrote my first paper I wrote for the 2013, and over the past 5 years, I've, just, something interests me, I'll find a website, I'll read about it, and if someone has made a claim that I can do with fairly simple math, I'll try to do something with it. So I've always kind of a fundamental is, I always like the tired light theories. I know that's heresy in the mainstream world. And I know there's a lot of them out there. One of them, or maybe a couple of them, might actually be right, but I believe that is much better than coming up with dark energy and shooting the galaxy into a big rip and all this type of stuff. So I figured I'd dabble with that a bit, and that's what led to this paper. Questioning the cosmological Doppler redshift. Linked with the concept of the redshift is an expanding universe with rapidly receding stars, galaxies, etc. Can a reasonably macroscopic and fairly tenuous form of matter like a star, let alone an entire galaxy, possibly travel at speeds approaching that of light and remain intact, except perhaps for something as dense as a neutron star? I don't believe in black holes. I read all of Crother's work and I agree with it. I do believe neutron stars are possible. I think Schwarzschild's analysis showed that there was a minimum radius that you would get, and maybe that's what a neutron star is, or if there are such things, maybe a quark star. I'm not sure about quarks. Quantum mechanics I haven't really played with very much. But certainly I don't believe in singularities. I believe there's some sort of minimum radius, maximum density, and neutron stars seem interesting and exotic enough to me that we don't need black holes. The only possible way to exhibit recession speeds approaching that of light would be for space itself to be expanding. Okay, so yeah, if you believe that galaxies are going out at 0.9 C or something, then yeah, space has to be expanding. I can't see galaxies and stars zipping along at that speed and everything remaining intact the way they do. Whether one accepts the traditional or Galilean Doppler redshift as the correct explanation. Galilean is a term I'll show you what I mean by that. I don't know if I invented it, but I'll certainly abuse it here. One is still left to conclude that something is racing away. A Galilean Doppler redshift may be an equally plausible explanation for those who adhere to the premise of stars, galaxies, etc., receding for whatever reason. Might this support one of the tired light theories? And I know there's probably I've come across at least a half dozen different theories since first encountering Marmot's website. I know Linda Ashmore has a lot of material on tired light. Assume Earth, effectively a stationary observer, receives a redshifted light from a star that's speeding away at 0.2c. The amount of redshift, the frequency reduction or wavelength increase based on the traditional formula would show an increase in wavelength 1.2, and if viewed as a cosmological redshift, the z value that they always calculate would be 0.2. All these calculations assume light travels at the fixed speed, c, and any redshift is due to a change in the waveform, that is, the shape of the wave, analogous to stretching the spring, not a change in the speed of light. And I mean, that's obviously how the Doppler shift works in air and in water, and so that's the analogy that's used there, even though they don't believe in ether, but they still use that analogy. And this is basically what the situation is here. The red circles are light from the stationary star. So if nothing's moving, the star's stationary, here's, you get x equals 0 and x equals 2, you get two full waveforms there. If it's moving, then the star would have started here, and by the time it got out here, you would have had this stretched. And so actually what you would have seen only 1.67 wavelengths here, so you would have seen the wavelength shortening, the wavelength was stretched, and so you would have a lower frequency because less wavelengths pass by, you have a redshift. So that's a traditional Doppler redshift. Waves, sound, water, etc., propagate as pulses through a medium where the matter, air or water molecules interact with each other to produce and propagate the pulse. Except for some longitudinal sound or transverse water movement among the matter itself essentially remains in place and just push, 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 push. These waves also have fixed propagation speeds given fixed physical properties such as temperature, pressure, density, viscosity, etc., and form the basis for the Doppler effect formula. Light has been assumed to behave similarly, that is, traveling at a fixed speed, again depending upon the medium and its properties, although for light in vacuum, no medium is deemed necessary. And Dick's talk yesterday talked about the electromagnetic field itself being the medium, and so light kind of creates its own medium, and I know there was debate on that, but for what I'm getting at here, you could accept either theory. Unless one returns to 19th century concepts of ether, and many who question the validity of Einstein's relativity have done so, what is the basis for assuming that light, if a wave, behaves in the same way as waves whose transmission is dependent upon the interaction of matter in a medium that can transmit pulses? Even if there is an ether, does it have to work the same way as water or sound? I don't know. Furthermore, why should the traditional Doppler effect apply to light, given that it is considered more than just a wave, that it's a quantum wave particle duality? It's not, no one knows exactly what light is, but kind of accepted it. It's sort of wave-like, but it's not really just a wave. If there is such a medium as an ether, why is it totally undetectable, other than theoretically its effect on light, or its movement being light itself? It would appear to have no physical properties, consist of no form of matter, etc. So if there is one out there, I don't know what it's made of or how it works. I know there's theories that it could be electric fields between galaxies, etc., and maybe that's right. But it's certainly different from the type of media you normally get with the types of waves we're familiar with. If light has no transmitting medium, why assume its wave behavior is analogous to waves propagating through a medium, for example, at fixed transmission speed, subject to the traditional Doppler effect? Why does light have to behave the same way? Why does the wave-like properties of light have to behave the same way as the wave-like properties of water waves or sound waves? Here's an alternative that I postulated. Assume that light retains some aspects of traditional wave-like behavior. What if the effect of the star receding at 0.2c acts directly to reduce the light speed to 0.8c, the Galilean transform, contrary to relativity, constant speed of light, etc.? Obviously, a theme here, I don't accept the constancy of the speed of light. Assume the waveform or the shape remains unaffected. There's no stretching. The frequency and the wavelength are the same, no stretching, but only the transmission speed changes. That is, it is reduced. A stationary star would still emit light at speed c, such that over an increment of time, t, you get n wavelengths of length w, would be received at Earth, your frequency would be n over t. A receding star would emit light at a slower speed, reducing the number of wavelengths to 0.8 n with reduced frequency. So even with you don't need to change the waveform to change the frequency. Changing the speed of the wave will change the frequency as well. This is an example here. Before, it's kind of hard, the red gets covered up by the green, but the red was the stationary star with 2 wavelengths. The orange was the traditional Doppler shift, which was 1.67 wavelengths measured relative to Earth. Now, if you have the Galilean, the star actually was here, for the star to be here when and analogous to the other ones, the star was actually here when it took off, and so what you get here is you get 1.6 wavelengths, a little bit different. So if the waveform, the traditional Doppler shift, it stretches the waveform. What I'm postulating is that you can keep the waveform the same, but by changing the speed of the wave, you can also get a frequency reduction because you get, because you get less wavelengths pass through there. The wavelength, you don't have to get, frequency reduction doesn't have to be stretching the wavelength if you don't vary, if you allow for the speed of the wave to change. And that's what I call the Galilean redshift here. There's no change in the waveform. The alternative is traditionally the length of the transmission is unaffected by the Doppler shift, and that it remains the same whether the star is stationary or receding. Its stationary length was CT. When it's receding length, again, you stretch the wavelength out. You decrease the frequencies, you still get CT, but you get a redshift because the shift is dependent on the frequency. If the speed of light is affected rather than the waveform, the receding length is shortened as follows. So I do a similar calculation, and what I come out with is I get 0.8 CT, and if I plug that into what's used for the Doppler effect Z value for stretching of the universe, I get 0.25, which is a little different from the 0.2 value that you get using the traditional. If my postulate was correct, the redshift would be a little larger for this particular example, but there'd still be a redshift. Since Z is used to calculate the star's recession speed, there would need to be another independent way of calculating that speed to determine which redshift estimate, the traditional, or the 0.833F from traditional or the 0.8F that I've calculated is correct, if either. Because I mean, if you just assume that the speed is determined by the frequency and all you can measure is the frequency, then you don't have an independent measurement of distance. So you would have to, in order to know what's right, you actually have the independent measurement of distance, and obviously we have no way of doing that with galaxies that are thousands of millions of light years away at this point. If the star is stationary, there is no Doppler redshift, and 2 full wavelengths, or cycles, are shown in the next slide as traversing the length over time t at frequency 2 over t. So this is just stationary star, very simple case. If the star is receding at 0.2 c, the traditional redshift, light still travels at c, elongates the wave so that only 1.67 wavelengths traverse the length over time. The frequency is 1.67 cycles per second, so the frequency is decreased from 2 to 1.67. Your cosmological redshift is 0.2, and one infers the star's recession speed to 0.2 c. So you've got some distant galaxy bombing away with a redshift of such a z. You say, okay, that galaxy is going away at 0.5 c. The universe is expanding, self-fulfilling to some extent. Assuming the emitted light experiences the star's recession only as a reduction in speed, the shorter length is traversed over time t. I get only 1.6 wavelengths. My frequency is 1.6 t, a little bit less than that. If this were assumed to correspond to the traditional Doppler redshift, I would calculate 0.25 c for the speed of my star. So if the waveform doesn't change, but the speed of light changes, the universe is expanding even faster, at least for this example. Oops. However, if the Doppler shift is Galilean, the speed of light transmission, not the waveform, is affected by the speed of the source, then the true speed of the star is 0.2 c. So again, we don't have an independent way to, unlike parallax where you have a way to estimate things, things are just too far away to get an independent measure of distance when you're dealing with the universe. So again, the red was the stationary star. The orange is the traditional Doppler redshift, 1.67 wavelengths, because it stretches out. The green is the Galilean redshift. The waveform doesn't stretch out, but because of the slowdown in the speed, you only get 1.6 wavelengths. Both of them are going to give you a redshift, but there is a difference in the amount of redshift, and if there was a way to independently measure that, then you could find out which one of them is correct, if either. Analogy with refraction. Traditional view for light refraction, when entering a denser or less dense medium, the speed slows or increases with the full effect of the speed change being carried by its corresponding change solely in the wavelength. That is, frequency remains the same. This is the normal picture they show you of wavelength, of the refraction. The wavelengths go down, but the frequency is kept the same. Therefore, there's no change in color, using this term loosely to apply to non-visible light, since color is determined solely by frequency. You'll often see that people use the change in wavelength to talk about color, but that assumes that you've got a constant speed. If the speed is allowed to change, as the case is here, the frequency doesn't change. It's a common misconception that color can be equivalently characterized by wavelength or frequency. The fact that there was no color change during refraction demonstrates that color is really a function solely of frequency, not of wavelength. Assume you're sitting by a swimming pool at midnight, gazing vertically upward at the full moon, which is made entirely of green cheese. Gazing upward through the atmosphere in the void of space for 10 seconds, the moon stays green, nothing happens. Now I take a deep breath, I dive under the water to the bottom, I look vertically upward at the moon for another full 10 seconds. After the water may be moving around, maybe a little blurry, but guess what? The moon stays green. There's no color change. Although the speed of light decreased when entering the water perpendicularly, so I'll eliminate the refraction aspect by looking straight up at the moon, only its wavelength, not its frequency dropped. There was no color change. In this case, transmission of light through different media, the speed change is carried by the wavelength, not the frequency. Frequency didn't change, it's still green as it was before. The two cases are different, however, from the galactic expansion. The moon and Earth are essentially stationary with respect to one another, over 10 seconds. And the light traverses two different media. You've got the atmosphere, then you've got essentially the void between the atmosphere and the moon. And then you got the water too. So you can treat the atmosphere and the void kind of similarly, and then you got the water. The speed changes considering the void atmosphere as one medium and the water as the other. But this change is carried only by a change in wavelength, not frequency, like in refraction. There is no redshift. The moon stays as green as ever. With the star receding relative to Earth, but the light not changing its medium, slight difference between Earth's atmosphere and the void of space notwithstanding, the density of air is going to have a big effect. A Galilean Doppler shift due to the decreased light speed is carried solely by a decrease in frequency. The wave doesn't stretch, but the length of the wave reaching the observer over the same time period is reduced. It's traveling slower, so you don't get as much of the wave. In the time period, the frequency is reduced, and therefore you would get a redshift. Whether one accepts the traditional or Galilean Doppler redshift as the correct explanation, one is still left to conclude that something is racing away. I believe the correct explanation for the apparent expansion of the universe is one of the various tired light theories, or maybe one that has yet to be proposed. Light's interaction with interstellar or intergalactic media reduces its energy, resulting in a non-Doppler redshift. And that's what a lot of the tired light theories will say, is that there's some loss of energy there. My goal has not been to resolve which tired light theory is most plausible, but to cast doubt on the traditional explanation of a cosmological Doppler redshift due to universe expansion. What I call a Galilean Doppler redshift may be an equally plausible expansion for those who maintain that everything is receding and for whatever reason. That concludes my second talk.
I like it.
Yes?
You mentioned Paul Marmot.
Paul Marmot, yes.
He's Canadian, and
Yeah.
he pronounced, because he's gone now, his
Marmay,
Now,
okay.
that's not my reason.
We're getting our pronunciations correct today.
Okay. He has a son, and his son is also a physicist. And some time ago, I also ran across Paul Marmay, and I made some inquiries. I wanted to get a couple of books of his, and lo and behold, I was funneled into his son. And we met at a conference, and we met in Ottawa, as a matter of fact. He's got his head screwed on, and if you ever want to follow up what you're getting at, tired light,
Yeah.
or some...
I mean, Paul Marmay wrote about a whole, tired light was just one thing. He's all over the place.
He
Really
was
impressive.
tremendously prolific
Yeah.
and well recognized in Canada, and then crossed the establishment, and it basically killed him. He lost his job, and
Because he opposed the standard. Yeah.
That's
Well, he
right.
was a traditional physicist, I mean, and then he went rogue, right?
Okay, but in any event, a roundabout way to get to the point I wanted to make, if you want to follow this up further, the tired light expansion of the universe, whether or not it's occurring, is a particular interest of the sun.
Okay.
And if you ever want to get in touch with the sun, let me know, and I
Yeah.
can give you...
Yeah, I would,
what
because
is necessary.
I say, I kind of owe my interest in all of this, NPA and now NPS, to having come across Paul Marmay's website I guess 5 years ago.
Yeah, okay.
Where's his son located in Canada?
In Ottawa. He
In
works
Ottawa.
for the National Research Council.
Oh, okay.
So
Okay.
he also harbors real concerns about a lot of mainstream
Right, right.
science. That's on the one hand. On the other hand, he's got a government job,
Yeah.
and he has to
Yeah.
walk that
Yeah,
fine
sure.
line that so many others walk.
The father won a couple of awards, didn't he?
Well,
Like, wasn't he
he
a
was-
distinguished physicist? It wasn't on relativistic work, I forget what his main area was
Well,
originally, but I know he,
He had many areas,
Yeah.
but yes,
He
he
won
was
some
given
awards.
the Order of Canada,
Yeah.
which is a very high award of recognition for
Mhm.
one's contribution to the work of society.
well, I know that when I came across, in my tired light adventures, I came across a website that was called QED, Quantum Electrodynamics, and the author of that website, Thomas Parvensic, I think is the name. And I corresponded with him, and I like, if they give me an email address, that's how I met Dick, is because when I came across his website and read some of his stuff, we started corresponding. So Thomas wrote back to me. He was kind of interested because I like tired light, and he had his QED explanation was something I hadn't come across before, and he sent me a paper that he was writing to review. And as I was reviewing it, I mentioned to him, I said, you have theory, I said, do you know that someone who would support your approach is Paul Marmay? And he says, oh, Paul Marmay, yeah. I said, oh, I want to definitely put that in my paper. So he was definitely, I think Thomas is from the US, but he certainly knew about him. Yes.
I think in terms of what your paper is trying to do, it's completely successful, I believe, in a very good way. What you're showing is that there is no way to get independent verification as to which is correct, which is the problem we face. But you also show that there are alternative ways that are equally plausible to produce the same results, and no way to absolutely independently decide on the two. And the message is that we really need to be careful about accepting what is accepted as being beyond question. Everything still is open to some question, and that's part of your message too. Is
Yeah, one of the
you
message-
can't be
yeah.
too sure about what's in generally accepted theory, because there are other alternatives that you can't prove don't apply.
Well, one of the even other themes I've really hit upon in the last 3 years and really pounded into people's heads to see what this group thinks about it And I gave a talk, and it's actually got quite a lot of views on YouTube. It's called, Consensus in Science. If you haven't taken a look at it, look up my name in Consensus in Science. It's, I think, a really interesting talk. One thing we don't do in physics is something that every other industry does, and that they have alternatives. If we're computer scientists, we have many computer languages to do the same thing. You can write something in Java, you can write in C++, you can write in PHP, Perl. We have some problem in physics with the idea of having 3 gravity theories.
Yeah.
And I think the reason is I have this sort of other theory, and that is, I write about it and talk about it, and that is, it seems like mainstream physics, what they want to do, what they are doing is discovering, and again, not being religious, but God's equations, or the universe's equations. So that when we come across F equals ma, or we come across E equals mc squared, we've now found one of the etched in creator's equations. Again, not being religious, just saying we're discovering the secrets of the universe.
What they discovered, you're saying they have religious overtones. The way
Well, it's not religious overtones. What it means is that physicists really believe that when you find the electron, and some things are going to be true. You find a planet, it's there. But when they find equations, or they come up with equations, that they're coming up with the secrets of the universe, meaning they're not alterable. You can't have 5 alternatives. You can't have 3 alternatives for the way light works. We have one. We're going to be doing hacking tomorrow. We have our particles, they're moving, the waves are encoded in pressure. We're going to try to do the whole universe with that. If we can make great predictions with that model, more power to us. But is that the only model that we can have?
Yeah.
So the question is we need to really think, I think we need all of us to continually think, is it possible that we will be living with multiple models that will do well? Some people's gravity model, like Dr. Lucas's, is good for one thing. My father's is better at other things. His is better at other things. So which one's right?
David, you put your finger right exactly on the main message that Ray made in this presentation, and that is we will have to live, if we are honest
Yes.
about putting the same rigor to each of the models,
Yes.
and there is no means by
Yeah.
which you can get the information to prove
Right.
one versus another, then you have 3 models or 4 models, which you have to consider and always use to see when new information comes along and kicks that model out. Now I've got 2 models.
Mm-hmm.
But then somebody else comes up with a good model and I've got 3 again.
Yeah.
But by a process of elimination, you take, as you learn new things, for example, as I pointed out in my presentation, you can't learn what made it different in 2 inertial reference frames without going from one to the other. If they remain in grand isolation, there's a whole lot of stuff you don't know, but once you go from one to the other, you know that delta P, momentum, is equal to M delta V. Not the difference, it's the change. And you get a different answer because you stepped outside of the methods that you've been using to introduce a new method, and it gives you new information of the type that's missing there. We probably can find it. We need to come up with a new way of building the experiment to look for that missing link. And if we think what we have is perfect, we'll never look for it.
Well, it's really amazing to me that if you look at NASA and you look at one of the things we expect, that NASA has a position of every body in the solar system down pat. And what they really do is they started out with one program and they continually put these tweaks into it when things aren't working. And they have to work the tweaks to make sure that it's sort of going. So they're looking at their observations saying our model isn't good. So they're constantly, the model is just, it's literally paper clips and string. And this is NASA using these calculations. They don't have one theory of gravity that is working and works well enough. And in my opinion, it isn't because they just started with one and it's just not superior. It's actually not a good one, and we can probably do better at it. But that goes to show you, when it comes to the practicality of launching these probes and going these directions, they have to, in engineering, know their calculations. as much as we think we understand even simple things like gravity, in calculating things in gravitational fields. They have to have on board, okay, we're getting to this point, we're going to make a correction, because where we think we're supposed to be, we're not, but we're planning for that, knowing that's going to happen. And yet in physics, we have this idea that we have to find the equation. Once we find it, we all bow down to it, write it on the wall, give ourselves prizes for it, and your name's in history.
Yeah.
And that's a problem.
That's a good point. And it also, I think, points the importance of something we touched on before, that is part of the message this kind of group carries, that science does not carry but needs very badly. And that ties to the open-minded thing, but businessmen who don't hold themselves out to be as smart as physicists have learned that if you have a problem nobody can figure out how to solve, you deliberately go out and get totally different trained people, biologists and physicists and whoever, specifically for the reason that they won't think alike. And it turns out those teams are very good at solving problems that no one discipline can solve, no matter how brilliant its people are. And that's part of the message we carry about being more open-minded, is look outside. Don't think what you know is absolute proof of reality. Get other points of view and test your own beliefs with an open mind. That's part of the message we're carrying to them.
Sure.
Don't just talk to yourself and believe what you know is absolute truth. Because you got to reach out and be open to other ideas in order to find the things that Ray's presentation says you have to have in order to progress and know which is right.
Okay.
In the paper, did you put your experiment in? I don't remember. Did you write the experiment in the paper that's in the papers? Because if you're talking about independent experimentation, if you read, I forget, it's probably your second paper, he's proposed an experiment to try, we always debate. He says when light is emitted, it's emitted from a point in space, according to Maxwell's equations, and it doesn't move with the source, and I'll move with the source. So he's proposed an experiment to try and settle that. And I have my own, and I have my rocket sled experiment. Dick volunteered to ride on my rocket sled, so I'm going to hold him to that.
You had a, Scott, go ahead, yeah?
Yeah, I think the problem with mainstream allowing alternative theories to their golden theories is that once they admit that these theories are not perfect, then that means other people can also come up with alternative theories. And then they've lost control.
They lost their power. Maybe their Nobel Prize isn't
and their system
important.
of funding and
the
people at the top will lose their jobs because, well, their supporting theories that just don't make any sense.
Yeah, one of the things I get constantly, I've mentioned this before, is when, especially with the public, with my movie, I get people come up and say, oh, there's problems in science. And I hear this from laymen all the time. They say, oh yeah, if there's a problem in science, all the scientists in the university, they get together and they look at it. And then they decide, well, our theories, they're going to have to be modified because this is different. And that's what they think is going on. But when you start to talk to them about the other stuff, like, well, that's not what really happens, then they either look at you think are conspiracies, they don't believe it. But when they investigate, it is a problem. But I like your phrase, golden theories. I'm going to use that. Okay, is that it then?
Yeah.
All right, thank you very much.